This video is about the fundamentals of artificial neural networks, which is what people usually mean these days when they talk about artificial intelligence. Large language models, image and video generators, image recognizers, some game playing bots, content recommenders like the YouTube algorithm, protein folding predictors, and many more. All of these systems are built from artificial neurons. So, to begin to understand how they work, we're going to focus on small systems with a single artificial neuron. And by the end of the video, we'll develop a solid understanding of what an artificial neuron is, the kinds of situations where it can be useful, how to get it to learn, and even though it'll just be one small building block, we'll still be able to see the core of how these larger systems work. And in the next video, we'll continue combining neurons to start to see how they can learn to perform more complex tasks. So let's begin with an overview of what an artificial neural network is at all. And then we'll dive into that single neuron example in excruciating detail. And it might feel excruciating, but there's no route to understanding that doesn't involve mental effort, so it'll be there if you want it. Anyway, artificial neural networks were originally inspired by natural neural networks, otherwise known as brains. Brains are composed of many tiny cells called neurons, which are interconnected into a vast network. A neuron can receive signals from other neurons, and if it receives the right combination of signals, it can fire, sending its own signal to other neurons down the line. And somehow, by connecting together many of these relatively simple units that process small pieces of information, the brain becomes capable of magnificently complicated information processing, which we call thinking, and some other things that we wouldn't call thinking. The brain gets its inputs from sense organs attached to neurons, and our muscles are also attached to neurons, which are effectively the outputs of the brain's processes. So, of course, there's a lot more to understand about the brain and the nervous system, but that's the basic idea. During the 20th century, we were starting to figure computers out, and the idea emerged that the brain could be viewed as a kind of computer, and that perhaps computer systems could use patterns inspired by the brain, using a network of small processing units, like neurons, that learn from experience. Artificial neurons. I'll link to a few of the early papers in case you're interested in the history, but we'll be focusing on the modern approach to artificial neurons, which is actually a bit simpler than some of the older approaches and much simpler than real neurons, but nevertheless, they have produced some very interesting systems. So, much like the brain, an artificial neural network has inputs. These inputs are numbers. Then the artificial neurons perform calculations, passing the results to other artificial neurons until we finally end up with outputs, which are also numbers. So they're mathematical functions. Numbers go in and numbers come out. And the function will have parameters that govern its behavior. So if you remember y equals mx plus b from your algebra class, that's a linear function where x is the input and y is the output, and m and b are parameters that govern the behavior of the function. M is the slope of the line and B is the vertical offset. And learning is just a process of adjusting these parameters until they fit whatever function is useful in whatever the situation is. So that's a simple function example, and a big neural network is going to be much more complicated with many more parameters, but it's still fundamentally a mathematical function, and learning happens by adjusting those parameters. So this leads to two big questions. First, how does that learning process work? Well, it works by trial and error, but how do you get a computer system to effectively do trial and error on its own? The answer is gradient descent. It looks like this. It's probably confusing, but we're going to build it up as we go, and it's going to make sense by the end. The second big question is, what kinds of functions or tasks can these kinds of systems perform? We'll go through some examples for one neuron in this video, and we'll also see what limitations those systems run into. And then for multiple neurons, it's of course broader, but we're gonna have to wait until next video to go into that. So our first system will involve a cannon. And our goal is to be able to predict how far a cannon shot will travel based on the initial kinetic energy of the projectile. The angle of the shot is fixed, and the only thing changing is the energy. So let's just shoot the cannon with a bunch of energies to get a feel for it. Okay, it turns out to be mostly a straight line, which is great because defining a linear function is exactly what a single artificial neuron does. The neuron remembers a number, a parameter called a weight. We'll give that weight an initial value of 1. Why not? The neuron will also take a number as an input, which in this case will be the projectile's initial energy. Then it'll multiply the input by the weight to produce an output, which in this case we'll interpret as the predicted distance the projectile will travel. So this is a function we can plot on our distance versus energy graph. It's a line, and the slope of the line is the weight. Comparing this line to the shot data we recorded, it's clearly wrong. These points are the actual observed data, so if the neuron were doing a good job, the line would go straight through the points. We could manually adjust the weight to get a good fit, but we're trying to build toward a system with a whole bunch of weights which we don't know how to adjust manually. Right? That's the whole point of machine learning, to get the machine to learn something we don't quite know how to specify ourselves. So the learning process will have several steps. First, we'll pick a random energy to test. Let's start with 20. Then we'll feed it through the neuron to get the predicted distance. Next, we'll actually fire the cannon with that energy value and see where the mango lands. We'll subtract the actual distance from the predicted distance to find the error in the neuron's prediction. So we've done the trial and we found the error. Now, lastly, we need to do that key part where we make an adjustment based on the error. If the error is a positive number, the prediction was too high, so the weight should have been smaller and we can adjust it downward. And if the error is negative, the weight should have been bigger, so we can adjust it upward. And for now, we'll adjust by 0.1. So let's let this process run for a bit. It turns out to work pretty well. It does keep overcorrecting since it's always adjusting by this 0.1. It would do better if it adjusted by a smaller amount, but then it would have taken longer to get in the right ballpark. This value is called the learning rate. And finding the right learning rate usually takes some experimentation to find the right trade-off between learning quickly and avoiding these overcorrections. So that's the essential idea with neural networks. You start with a function with random parameters, then repeatedly test how it works and adjust those parameters as you go until it starts calculating good results. Just trial and error in program form. That's the core idea. But as you might imagine, there's a lot more to say about how this process needs to work in a more complex scenario. So let's make this slightly more complicated by moving the cannon forward 30 meters. We're still measuring the landing positions from where the cannon used to be, but it's shooting from up here now. If we collect some data from this situation, we get a line with the same slope as before, but now it starts at a distance of 30, since that's where the cannon is. If we try to get our neuron with one weight to learn this new function, well, it can't really do it. It can only learn lines that pass through 0, 0. We can fix this by adding another parameter to the neuron called a bias. The bias will just be added to the neuron's output and not multiplied by the input. So now this neuron can make any line, right? We're back to y equals mx plus b, except it's w instead of m. But anyway, the system's job is to learn the right values for the parameters, allowing the function to fit the data. So let's try training this the same way we did before. If the prediction is too low, we'll turn the bias up, and if the prediction is too high, we'll turn the bias down. Same rule we used for the weight. I also want to make the training a little bit more efficient. You may have noticed that this step 3 of finding the actual distance takes most of the time in the training loop since we have to wait for the mango to land. So instead of doing that during the loop, we'll just collect a bunch of data ahead of time, and then each time through the loop, we can just pick a random data point and use that. Okay, so let's see how this works. As I foreshadowed, it turns out to not work. What this line really needs is to have a higher bias and a lower weight. But since the weight and bias are following the same update rule, they always change the same way at the same time, so they're stuck together. What we need is a different adjustment policy, one that allows the two parameters to be changed differently. To figure out a way to do that, let's examine a little bit more closely how the error is affected by the weight or the bias. We can write down the error calculation directly in terms of the weight and bias, right? Same thing as before, just written down differently. So in a certain trip through the training loop, all of these pieces have specific values. But when we're thinking about adjusting the weight, we're saying if we allow the weight to vary from the current value with everything else staying the same, how would that affect the error? So we're actually thinking of the error as a function of the weight here, and we can graph that function. So here we can visualize our current adjustment policy. Since the error is positive, we decrease the weight, and the error we would have gotten would be smaller, closer to 0, which is what we're looking for. And if the error were negative, we would adjust the other way. Right? This is the same adjustment policy we've been using, we're just looking at it on a graph. For the new approach, the key thing is to notice that the slope of this error line changes depending on what the current input energy is. If the input energy is high, like it is here, changing the weight has a big effect on the error, but in a situation where the input energy is low, changing the weight would have a smaller effect on the error. So instead of always adjusting by the same amount, we'll adjust based on this slope value. This makes it so we automatically adjust more when it'll make a bigger difference, and this slope value in this case happens to be the same as the current input energy. And that was an important point, so if you're at all uncertain about it, it's a good time to pause, rewind, perhaps even think about it. In the general case, you find the slope of a function by taking the derivative. If you're not familiar with derivatives, that's fine. The derivative is just the general way to figure out how steep the function is at a given point, even if we had some complicated curvy thing going on. So that's looking at the weight, but the error is also a function of the bias. And we can also graph that. And now instead of a line, it's a plane. And we can think of this as the error landscape. As we adjust the weight and the bias, we're moving to different points on this landscape, trying to find an error as close to 0 as we can get. And this plane sort of has two slopes, one with respect to the weight, which we just looked at, and one with respect to the bias. The bias just adds directly to the prediction and also the error. It's not multiplied by anything, so adjusting it just has the same effect regardless of the input energy. So the slope with respect to this bias is just 1. So when we adjust the bias, we'll adjust by the learning rate multiplied by 1. Of course, multiplying by 1 doesn't do anything, but just to keep it symmetrical with how we're adjusting the weight, we'll leave it there. Okay, now we're almost ready to try out this new derivative-based approach or slope-based approach, but we should tweak the learning rates a little bit. This is sort of cheating since you normally wouldn't know this ahead of time, but things will go more smoothly if we reduce the learning rate for the weight and increase the learning rate for the bias. Right? Normally, you would have to experiment a bit to find the right trade-off between fast learning and avoiding overcorrections, but I thought I'd just spare us that for now. Anyway, let's see how this goes, and we'll just reuse the same data from before. And hey, it ends up working pretty well. We could turn the learning rates down to refine the result a bit, but this is good enough for what we're trying to do. And you might see a resemblance between this adjustment rule and the preview of gradient descent I showed earlier. And it's essentially the same thing, but there's a few adjustments we can do to make them match. First off, we're treating the weight and bias in the same way, so we don't really need to list them out as separate parts of the process. We can unify the adjustment statements by just saying we adjust each parameter by a learning rate times the derivative of the error function with respect to that parameter. Okay, and one last thing. We currently have a slightly different rule based on whether the error is positive or negative, but it would be nice to just have one rule that we always follow. So instead of working with the error, we'll calculate the absolute value of the error, which just means that if the number would be negative, treat it as positive. So now the function output is never negative, so we never need this rule for when it's negative. At first, it might seem like we're throwing some functionality away here, but it'll actually result in the same exact adjustments as it did before. In places where the value flipped from negative to positive, the slope also switched, but in the other direction from positive to negative. So in those situations, the parameters will still increase just like they did with the other rule. So that was kind of confusing thinking through the swapping of the negatives, but this does have some nice properties. First, we now just have one adjustment rule, right? That's what we were going for. That applies to every parameter every time through the loop, regardless of the data we're learning from. But the really powerful part here is that conceptually, the rule just boils down to going downhill on this error landscape. We find how the landscape is sloping and we go downhill a little bit at a time. And this should get us to small errors, which means accurate predictions. And this is where the term gradient descent comes from. Without getting too formal or going into different usages of the word, a gradient is the same idea as a slope or a derivative, just applied to functions of multiple variables. Okay, and there's one final tweak to make this fully general and match that gradient descent rule from the beginning. This function, the absolute value of the error, applies to this specific scenario, but in different scenarios, you might need a different kind of function to capture how well the system is doing. The general name for these functions is loss. Loss functions can take many forms, but they're always some function where lower output values means the network is performing better on your data, right? You want to lose less. It can be a challenge sometimes to figure out what that loss function should be for your situation, but once you find a good one, you can train a neural network to descend in the landscape defined by that loss function, and then it will learn to perform the task. So at long last, that's the universal rule for how these things perform trial and error. For each parameter in the network, we'll find how the loss function is sloping with respect to that parameter, and then we'll go downhill a little bit in that direction and repeat. Okay, so that's the Cannon predictor, and that's gradient descent. But there's still more to learn about what a single neuron can do. Next, we'll give our single brain cell here a more common type of task for neural networks, which is to classify data into different categories. For example, classifying images was one of the first tasks people attempted to get neural networks to do. But we're only working with a single brain cell here, so we won't be able to classify full images. Instead, we're going to classify mangoes. So I went to a grocery store and bought a bunch of mangoes of 3 different types. We have 5 Tommy Atkins mangoes, 5 Malika mangoes, and 5 Namdok Mai mangoes. And I measured each of their lengths. If we sort all of these lengths, we can see that the Tommy Atkins mangoes were all shorter than all of the other mangoes, so it should be relatively easy to tell whether a mango is Tommy Atkins by just looking at the length. Again, we could solve this problem ourselves pretty easily. If the length is less than 12, it's Tommy Atkins, otherwise it's not. But we want to see if we can get the neuron to learn that on its own. So let's step through our training loop process and see how it looks in this situation. So we've collected the data, but before we can actually train the model, we need to prepare the data. The neuron is going to output a number, so we need to turn these mango identities into numbers. That way, we'll be able to make some comparisons when doing the trial and error loop. Yes, Tommy Atkins will have a value of 1, and no, not Tommy Atkins will have a value of 0. There's nothing special about this system. Other choices could work just fine, but it does feel intuitive for 0 to be no and 1 to be yes. And now that the data is all numerical, we can graph it. So let's give our neuron an initial weight and bias. This neuron's function takes in a length and spits out a category prediction. And just like before, it's a linear function. If we try to predict the longest mangoes category, we put 18.1 centimeters into the neuron and we get 2.05 out. What does this mean? 1 means Tommy Atkins and 0 means not Tommy Atkins. So in that system, what would 2.05 mean? Well, I don't know. The issue is that the neuron can output any number from negative infinity to positive infinity, but our data has values from 0 to 1. So we need to figure out a way to map from one system to the other. There's lots of ways we could do that mapping, but a common way that'll work out is to use a function with a great name called a sigmoid. If you put 0 into a sigmoid, it gives an output of 1/2. And if you put a larger and larger positive number, the output gets closer and closer to 1. And if you put in bigger and bigger negative numbers, the output gets closer and closer to 0. Effectively, it squishes any number onto a scale from 0 to 1, and that matches the range of our data. So we can add an extra sigmoid step to translate the raw output of the neuron to a scale from 0 to 1. With our previous value of 2.05, putting that through the sigmoid gets us to about 0.89. We could interpret that as the neuron saying it's 89% sure that the mango is Tommy Atkins, or it could be something else, but the main point is that it's between 0 and 1, so up clearly means more Tommy Atkinsness. Turns out it's actually a Malika mango in this case, so the neuron has some learning to do. But now that the number systems match, we can write a loss function. And we can actually use the same pattern as before. We'll take the prediction value after it comes out of the sigmoid, that's the prediction value, then subtract the real value and take the absolute value of that. And we might as well write it all out in terms of the weight, the bias, and the input. And the last part of the training loop will be to make an adjustment based on the slopes of this function. To dig more into that, let's again graph the loss as a function of the weight and the bias. The idea, like before, is to step downhill on this landscape. At the initial weight and bias we picked, we're actually on a pretty steep spot on this landscape, so the neuron should be able to start learning right away. But this is just the loss function for one of the data points, right? Just like before, the loss function depends on the data point we're looking at as well. So if we make a little room here, we can actually graph a separate surface for all 15 data points. In all of these graphs, the dot is showing the same weight and the same bias, but the loss value shown by the height of the surface varies. The top row corresponds to the Tommy Atkins mangoes, and notice how those functions are sort of opposite of the others, and that's because the actual value in the loss function is 1 there, but it's 0 in the other ones. All right, now that we've thought through how the training will work here, we can let the computer do its thing, looping through the process. We're going to be reusing our data many times here, and when you've gone through all of your data once, that's called a training epoch. So after one epoch, the prediction function with the sigmoid lays down almost completely flat. Effectively, the neuron has learned to just say no, not Tommy Atkins, and this does make it get 10 of the 15 right. And if we look at the loss surface plots, we can see that we've gone downhill for the Malika and Namdakmai surfaces, but we've actually gone uphill a little bit on the Tommy Atkins surfaces. There's just more of the non-Tommy Atkins mangoes, so the learning has favored them. So that doesn't seem like such a great start, but let's throw more epochs at it to see whether it can learn to get them all right, rather than just the no's. It turns out if we go all the way to 100,000 epochs, it's still predicting no for everything. The weight and the bias have hardly moved, and that's because we're in pretty flat spots in all of these loss surfaces. There's just not much of a hill to go down, but even though the change has been slow, it hasn't been actually 0, so let's keep going. After 10,000 more epochs, still not much movement, but if we do 10,000 more, going all the way to 120,000 epochs, it turns a corner, and suddenly the predictions are mostly right. For lower length values, the output is close to 1, and for higher length values, the output is close to 0. It still has some improving to do. For example, it's only about 95% sure about this longest Tommy Atkins mango, or however you want to interpret these intermediate values. But if we pile more epochs on, it does get more accurate. So we've successfully trained this neuron to identify the Tommy Atkins mangoes in this data set based on the length. It wasn't the most efficient thing, and there are things you can do to make it more efficient, but we got there. So we could be done here, but I do think it'll be helpful to look at one other system we could have used to see why that would not have worked. If we go back to the raw output of the neuron without the sigmoid, we can see a more direct interpretation of what the neuron is doing. For lengths below about 12.5 centimeters, it's outputting a positive number, which we could interpret as meaning Tommy Atkins. And for lengths above that, it's outputting a negative number, meaning not Tommy Atkins. So we could have made that our rule in the first place. Positive numbers mean yes, and negative numbers mean no. The trouble here, though, is that the transition is too sudden. If we put that into our loss function, these loss surfaces would become completely flat regions with zero slope, meaning they're useless for training. And we also have these completely vertical parts whose slope is sort of infinite, and those are also useless for learning. So we needed to use this sigmoid, or something like it, to allow us to interpret the neuron output more gradually. Okay, so we've accomplished that goal. Let's move on to another. So I also measured the mass of these mangoes. And here's the full scatter plot. Like we saw before, you can tell which mangoes are Tommy Atkins just by looking at the length. And it turns out you could also tell which are Namdok Mai just by looking at the mass and ignoring the length. If we wanted to, we could set up another neuron to be a Namdok Mai recognizer, but that process would be exactly the same, just using the mass instead of the length. So let's skip that. Feel free to do that on your own with this data. It's right here if you'd like to do it. But it'll be a bit more interesting to try to make a Malika recognizer that has to look at both length and mass. So first things first, we should label the Malika mangoes as 1, since those are now the ones we're trying to detect, and relabel the Tommy Atkins ones as 0. Our neuron is also going to need a second input, so it can also look at the mass of a mango. And now that it has a second input, it'll also need a second weight. To get the output, the first weight and the first input are multiplied together, just like before. And then we also multiply the second weight and the second input together, add that, then we add the bias, and that's the output. And this pattern, I think, makes it make slightly more sense that we're using the word weight for these parameters. The output of a neuron is the weighted sum of the inputs plus a bias. And if we had 3 inputs, we'd have 3 weights, and so on. The raw output of this neuron now creates a plane. It's very steep because we kept the previous weight for the length, and just like before, we could interpret positive values as yes and negative values as no, but to get the learning to work, we'll need a more gradual system of interpretation. So if we put it through a sigmoid, that'll map those unbounded values to a range from 0 to 1. So right now, this neuron is classifying all of the mangoes we have as Malika, and it would only say that a very long and very light mango is not Malika. So that's wrong, but it hasn't had a chance to learn yet. And the loss function also needs to be updated to reflect the new prediction calculation. Unfortunately, we can't graph all the loss surfaces in the same way we did before. That second weight we added would turn all these graphs from 3D to 4D, which we can't really do. But even though this loss function involves more dimensions and we can't graph it, it still has a similar character, and that same downhill idea is still at play. So let's keep showing one of the old surfaces just as a reminder of the overall idea. Okay, so as for the training, I tried it starting from here, and after many billions of epochs, it was still nowhere near close to classifying these correctly. So it's even more inefficient than it was before. There are some ways to improve the training performance. This video isn't really about practical training approaches though, so I'm just gonna list them here so you can look them up if you like. But instead, we're just gonna cheat a bit by giving the parameters values close to what they should actually be in the end. Okay, so now let's let the training loop do its thing. Just to be sure, I let this one run for 1 billion epochs, and it ends up here, which, well, you can see it was trying. It does get most of the mangoes right, but for the shorter and lighter molecules, it's clearly confused. The problem is that a single neuron can only make a single straight line. There's no line you can draw through this data to separate the molecular mangoes from the rest. So we can't do a good job here with just one neuron. A more pure version of this problem is the exclusive OR task, or more commonly called XOR. It's a binary function that works like this. Given two inputs, each of which are yes or no, it outputs yes if one of the inputs was yes, but not if both of them are. That's the exclusive part. If, like before, we treat no as 0 and yes as 1, graphing the data looks like this. You can't draw a line that separates the yes and no outputs from each other. So a single neuron can't learn to perform this function. It always gets at least one of the outputs wrong. To get them all right, we would have to do something like this, and one neuron just can't do that. This fairly simple XOR function demonstrates the limits of a single neuron. In cases where you can't solve your problem with a straight line, a single neuron won't help you, like with our mango example. This isn't too surprising given how we came at it. A neuron is a linear function, so of course it can't learn to do nonlinear things. And this idea turns out to apply to higher dimensional problems where you might have a row of many neurons, each with their own output. You're always going to be making some kind of linear function, and there are going to be many kinds of problems it can't solve. And that's it, at least for one neuron. I'm going to review what we've seen here and give a quick preview of the next video on multiple neurons, but first I need to thank everyone who supports this channel on Patreon. Thank you. If you appreciate these videos and have some budget to spare, I'd love it if you'd consider supporting. The first tier is $3 USD. That gets your name in the video, like this. There's also a $10 tier for patron-only live streams, and those happen 1 week after each video is published. In those, we can go through things in a bit more detail and answer any questions you might have. It's really driven by the people who show up. And this channel couldn't exist the way it does without viewer support. Notice there's no sponsorships. So I really do appreciate everyone who supports, but I understand that not everyone has the budget, and that's fine too. I'm just glad you're here. You're here till the end. That's pretty great. I'm excited about that. Anyway, back to reviewing the video. So, artificial neural networks are mathematical functions. Those functions have parameters which start out in some random place, and they're adjusted through trial and error in a process called gradient descent, until the function fits whatever data you're training on. That's how they learn. And for a single neuron, it's just a weighted sum of its inputs, which, if you graph it, makes a line, maybe a plane or other higher dimensional version of a line, but it's a line. And we can take that linear function and transform it to solve problems like binary categorization. But at the end of the day, a single neuron can only make a line, which puts limits on its usefulness. In the next video, we're going to learn about systems with more neurons, and we'll see that adding more neurons can allow us to make much more versatile functions than just straight lines. And we'll talk about an extra ingredient to the learning process that allows those more complicated systems to learn, called backpropagation. And I'll also probably rant about how we're all doomed. Maybe, we'll see how it shakes out. Anyway, I'll see you then, and thanks as always for watching until the end.